Good morning to everyone. This is Dr. Polaiah, working as a professor in the Department of IT, Institute of Aeronautical Engineering, Hyderabad. So I'm very glad to inform you that one of the important topic on spatial enhancement by combining methods, which are help us to understand in terms of image processing uh, towards to the spatial enhancement application process. So there, how we can introduce this spatial enhancement by combining method in this sense, though we are all aware about frequency domain and time domain. So here we are going to be understand such a domain importance in terms of spatial enhancement by combining methods. Let me going to see one by one. So what does it mean the combining spatial enhancement methods, which are in terms of enhance this image by sharpening it and by bringing out more of the skeletal detail. The narrow dynamic range of the gray levels and high noise content make this image difficult to enhance. The strategy we will follow is to utilize the Laplacian to highlight the fine details and the gradient to enhance prominent edges. The image shown below is a nuclear whole body done scan used to detect diseases such as bone infection and tumors. For reasons that will be explained shortly, a smooth version of the gradient image will be used to mask the Laplacian image. Finally, we will attempt to increase the dynamic range of the gray levels by using gray level transformation. This is called spatial enhancement process. So where we take such a enhancement process, one of the best example is here. We are applying some combining methods, which we can call as combining spatial enhancement methods. So this combining spatial enhancement method, major goal is enhance the image by sharpening it and by bringing out more of the skeletal detail. So image of the whole body done scan. Let you can take the A images this. And when we apply the Laplacian is B. C is you are going to be sharpened, and D is you are applying combined spatial enhancement method, which we simply call as Sobel gradient method. So that means where we combine here, so we compare A with D so that we can understand how this gradient method has been working in terms of you are increasing the or enhance the your required image. We compare both. So coming to the another extensionally example. So here still we going to be see the previously what we called as previous example and present example is here. You are considering enhance the image by sharpening it and by bringing out more of the skeletal detail. That is what we are concentrating here. That is what here concentrating here. Okay, so such a method we can understand in between these two and in between these two, which we are going to be understand by the help of that spatial enhancement based on the combining spatial enhancement methods. Okay, so here we want to understand that the meaning of spatial combining methods, that is nothing but combining spatial enhancement method, how we can define in the sense. So we are here we are concentrating one of the principle that we call as the neighborhood pixel comparison principle. So that means the neighborhood pixel which we are going to be concentrate by the help of one of the function objective function with respect of x and y coordinates. So this x and y coordinates of the function which we are called as here, such a one we are going to be see here that neighborhood of the process completely is defined as any area bigger than the single pixel, maybe of any size or shape. So most used rectangular or around the central pixel might be referred to as filters, kernels, and templates, which we are going to be concentrate in terms of your image enhancement. So here we are also going to use the Windows method also. So coming to the let you can see there what you mean to understand that the linear filtering process is here, which we are concentrating by the help of one point p of x, point x comma y in the image is we are comparing one another. How in the sense as we require that we take in the pixel and intensity in terms of your object function of x comma y, which we are concentrating on mask on part of the image, which we are going to be see that by applying this method as we call combining spatial enhancement method, which can be understandable in terms of r equal to w of minus 1 comma minus 1 f of x minus 1 comma y minus 1 plus w of minus 1 comma 0 f of x comma x minus 1 comma y. That is what we are extended each and every situation. For example, this situation, what is your window value? This situation, what is your window value? This situation, what is your window value? Like that, we extendedly concentrated here. Next, another important point is here smoothing linear filters. The output response of a smoothing linear spatial filter is simply the average of the pixels combined in the neighborhood of the filter mask. These filters sometimes are called averaging filters or low pass filters. So, averaging filter is you are taking as one of the masks that mask of the part of an image which we are going to keep into the filterization and finding average value of your number of rows and columns multiplication. So based on this, we are going to be understand how your filtering is also one of the very important. So average filter is also called as box filter. So if you go to the weighted average, which is we are keeping on to the multiplication of your factors, and will be attained your required value of the filter mask value. So let us see here, for example, combining spatial enhancement method is also concentrating by the comparison of neighborhood pixel process, which we call neighborhood pixels concept. So here we are using original image of size 500 into 500 pixels, 500 into 500 pixels. The marks of sizes n is equal to 3. So what is the n? This n is the what we are understandable in terms of your concentrating. That means you are calculating of your particular mask size of the part of an image. Okay, the part of an image in the sense the image which we are concentrating as gray level image, which is right now concentrated more and more based on this mask value of n only. So that is previously we have gone through that to find out the value of average filter or weighted filter average value. How we calculate this completely depends on the masks of the sizes from your image. So the we also concentrating here such a filter which we discussed the linear filters. Sometimes we those filters are maybe failure because it's a linear. So, but the world is a non-linear process, obviously, because it is image processing, concentrating which we are process from the world application only. That is a global application. So here, such a linear filters process may not be constant. So that's what we go to extend such a combining spatial enhancement method in order to statistics filters or nonlinear spatial filters whose response is based on ordering the pixels contained in the image area encompassed by the filter, median filter, max filter, min filter. So what do you mean to understand median filter is for removal of salt and pepper noise we are using median filter. For finding the brightest points in an image is an image. Min filter is used for the opposite purpose. Is right now we are playing 10, 20, 20, 15, 20, 20, 25, and 15. This is the number which we are getting from the one of the mask size of the image. Those values we want to shorted, we can be shorted. In this sense, the redundancy values of your calculated values may be find out by the help of your such a encompassed by the filtering process. What are those? For example, median filter output is 20, maximum filter output is 10, and minimum filter output will be 100. These are which we are applied right now. So here let me take example which we can apply your averaging filter process, your nonlinear process by the help of your median and maximum and minimum filter process. We are taking the one of the example X-ray image of the circuit board corrupted by one of the salt. What that means? One of the type of noise is here salt and pepper noise. So salt pepper noise is also one type of noise which we can understand from your scanned image. So your scanned image not be visible because it is original. Let us take this is original image. Okay, this is original image. So such a image, the noise reduction with a 3 by 3 averaging mask, noise reduction with a 3 by 3 median filter. So there is what we can understand that such a original image which we copied from the one of the references here. Such a noise image process we can concentrate much more on the your required filtering process. Comparing this to this and this to this, you are averaging mask and median filter how it is work. So which one is more giving more clarity of the image processing? So coming to the such a combining spatial enhancement method is also extending in terms of sharpening is to highlight the fine detail in an image or to enhance detail that has been blurred either in error or as a natural effect of a particular method of image acquisition. Image blurring could be accomplished in the spatial domain by pixel averaging in a neighborhood. Since averaging is analogous to integration, it is logical to conclude that sharpening could be accomplished by spatial differentiation. So that is, we can define in order to first order derivative of an one-dimensional function f of x is here in terms of dou f by dou x equal to f of x plus 1 minus f of x1. So this is first order differential equation. So what do you mean to understand that mathematical model of the your sharpening spatial filter is also known as derivative filter. That's what they are written such a mathematical formula. The purpose of that spatial filter is just the opposition of the smoothing spatial filter. It is the main focus in on the removal of blurring and highlight the edges. It is based on the first and second order derivative. So you can also derivate the your previous spatial filter nothing but differential filter to extend as a second order derivative filter. So that means you taking this is what we call as one dimensional that we are first order. This is f cap is first order. Okay, so such a first order derivative must be zero in the plot segment, must be non-zero at the onset of the gray level step, must be non-zero along ramps. First order derivative in 1D is given by is this equation. Is this equation. So the second order derivative must be zero in flat areas, must be zero at the onset and end of a ramp. So you can understand here, ramp signal will be applicable from second order derivative. So where step signal is applicable to the first order derivative. So that means you must be zero along ramps is nothing but second order derivative in one dimension is given by f double dash, nothing but second order differentiation is right now extended f of x plus 1 plus f of x minus 1 minus 2 f of x. The common sharpening filters also, we had to understand that how we combining spatial filter is used for enhancement of an image is the same. Similarly, the sharpening filters which are unsharp masking, high boost filtering, gradient, that is first order derivative, Laplacian, that is second order derivative process. So useful for emphasizing fine details that we are considering here. The elements of the mask contain both positive and negative weights. The mask element sum to 0 is, if we calculate this value is 0, then we are going to be understand that the positive, and if it negative, negative. So like that we are going to be find out the required value. So emphasize size edges in an image which we are going to be calculated according to the your selected mask, selected mask, selected mask part of the gray levels value. For example, let you take the in between these two image, input image and sharpened image. For better visualization, the original image is typically added to the sharpened image. Sharpening filters is also extended as we discussed on sharp masking and high boosting filters, which also concentrate here first. Obtain a sharp image by subtracting a smooth, that is low pass filters image from the original image. That is contrast enhancement has been applied for better visualization. So image hair sharpening emphasizes edges, but details are lost. Add a weighted portion of G of mask, that is gray level of the image. We concentrated one of the portion. We added as a weighted portion of G mask back to the original image. Then we compare that when unsharp masking is concentrating your value of the K is 1. This process is known as high boost filtering when K is greater than 1. So see that example is here. See that example is here with K value. So that we are going, when K equal to 1 is here, we'll get the output. Okay. So high boost filter example, we also can understand here such a combining spatial, sharpening spatial filters is here high boost filtering example. Let you take the original signal and blurred signal, unsharp, unsharp mask and sharpened signal. See here there is a linear. Here there is a linear. So based on this one-dimensional example, signals we are going to be concentrate A, B, C, and D parts of image, or we can check together. Okay. So sharpening spatial filters is concentrate on original Gaussian smooth G mask. Unsharp mask is nothing but 1. High boost filtering is greater than 1, and it is nothing but a 2D example. So we can also extend this sharpening spatial filter as a part of combining spatial filters enhancement purpose, which we are concentrating foundation, Laplacian operator, unsharp masking, and high boost filtering using first order derivatives for nonlinear image sharpening and gradient operation. So first order derivative of the one dimensional function of x is the difference between your second order and your second order and first order. We see here this is first order, this is second order, which we had discussed earlier. If second order isotropic derivative operator applied in terms of Laplacian for a particular function of the image is here dou square, that is sigma square of f is equal to dou square f by dou x square. This is nothing but gradient value. This is nothing but gradient. We call as gradient square or that capital sigma. So that gradient value is changes according to the second order of the selected image of the object function. So this object function we can extend first order, second order with respect to x, with respect to y, and combine together. So we'll obtain your required. Such a equation which we are taking here based on your selected image is right now filter mask used to implement such a equation which is previously equation, that is previous equation, previous previous equation, which is right now we have gone through the dou square, what is that? Dou square f function, that is f function, RG. So according to this, we calculate your x and y values, and we are going to be see the mask used to implement in the extension of this equation that includes diagonal terms, where we can also concentrate in two other implementations of the Laplacian found frequently in the practice. We also extended one more equation that we called as using what we call Laplacian equation. So here g of x comma y is equal to f of x comma y is c is equal, here what we call corresponding to the previous equation, where we call as some constant parameter, maybe -1 or equal to 1. When -1 is you are corresponding to the your what we call the sharpening filter in terms of mask part, where equal to 1 we called as a two filters is used. So you can see this sharpening based on your Laplacian method scaling, Laplacian with scaling image is sharpened using the mask in the figure. Such a resultant of the image is passing here from the original. So we can understand this that complete images are the concentrated in environmental department at the NASA center. They have been used in our apply techniques. So yes, we are right now concentrating not only simply masking methods, but unsharpening masking and high boosting filter. Whenever we are considering nonlinear filtering process, we are using these two. So unsharpening mask means sharpen the images consist of subtracting and unsharp. Nothing unsharp is nothing but smooth version of an image from the original image. For example, printing, publishing industries process, there are three steps they are following. Step number one, blur the original image. Two, subtract the blurred image from the original. Three, add the mask to the original. So you're going to see that let f dot x comma y denote the blurred image. Unsharp masking is g mask of x comma y equal to f of x comma y minus f dash of x comma y. Then add a weighted portion of the mask back to the original. Is right now concentrating your k value. So similarly, we can go through the unsharpening process. So these are the example which we want to concentrate. Image sharpening based on first order derivative. So we are going to be seeing your gradient of f is equal to gx gy, where we can concentrate the g to f. We can transform. The magnitude of this vector g, that is gradient f, denoted as m of x comma y, where m is nothing but magnitude of your gradient objective function, is simply be calculated as square root of g square x plus g square y, is help us to get your required of the image. So as our title is, we are considering different methods. One of the method we also called as a robots cross gradient operators, which we are going to be concentrate for Sobel operators. So here M of x comma y is nothing but which we are concentrating much more on your g values. So your see that sharpening spatial process from the one figure to another, you can understand in easily. Okay, so I hope you understood our topic, that is combining spatial method for the sake of enhancement. Simply called as combining spatial enhancement method, that we also called as enhancement purpose. We are using by combining methods based on the different linear and non-linear filters. I hope you understood the simple concepts with the simple examples and based on some mathematical models process. Then, if you want further refer, kindly go through these references. From this fundamentals of image processing textbook, we can have a simple understanding. I'm very thankful for your attention on understanding this simple concept, and we can continue our discussion with other important topic which covers from our image processing. Thank you so much for your concentration. Thank you.